Welcome back to the lesson on transducers. Just a quick summary of the first lesson. So transducers are components that are able to convert non-electrical signals, and some of these signals we are talking about is like sound, temperature, light, yeah, and it's able to convert all this into an electrical signal. And why we do this is because circuits, they only recognize electrical signals, whether they be analog or digital. Okay, and then if they are able to convert from non-electrical to electrical, and I also told you that they would also be able to do it backwards. Yeah, so typically these are your input transducers and these are your output transducers. Okay, so this is what we learned in the first video. Now we are going to go into specific transducers. So in this case, I want to talk about temperature. How do we monitor temperature? So the component that we're going to be talking about today is called the thermistor. I'm sure some of you have heard it. So what is a thermistor? Okay, so same thing, underline. So a thermistor is a resistor that changes with temperatures. And there are two kinds. One is a negative temperature coefficient, short form NTC, and the other is called a PTC. All right, you have to know how to draw the symbol. You have to know how to draw the symbol for NTC, and also to know how to draw the symbol for a PTC. So the only difference, NTC is a negative sign here, a PTC is a positive sign here. Okay, so these are how NTC and PTC looks like. There is no polarity, so you can plug it in any way you like it. And let's find out how they work. Okay, so a lot of times you're going to be commonly using the NTC. So we'll talk about the NTC, but then I'll also do a quick explanation for the PTC later on. Okay, so for the NTC, so this is the characteristics graph. Now you notice that when the temperature is low, when there's a low temperature, the resistance is very high. But as temperature increases, you realize that the resistor decreases. So a very high temperature gives you a very low resistance, and a very low temperature gives you a very high resistance. Okay, so this is a NTC. Now, a PTC, so this is your NTC. A PTC, a resistance temperature graph, would look something like this. Okay, so it's just the opposite. All right, so a PTC, low temperature, low resistance. This is your R, and this is your temperature. Sorry, capital T. Low temperature, low resistance, high temperature, high resistance. All right, so just know the difference between your PTC and your NTC. So, excuse me. So how do we use the NTC and PTCs as temperature sensors? Yeah. So what we want to do is we need to take the ambient temperature and kind of convert that into a electrical signal. So it's used in places like refrigerators, air conditioners, where we need to have some sort of a temperature control. Yeah, so you see this in the supermarkets, the fridges, and this is how we usually do it. So we usually do it as part of a voltage divider. So let's look at this. Yeah, so this voltage divider formula should be very familiar to you right now. Okay, So let's take a look here. Remember, this is a, if I find a negative sign here, this is a NTC. Okay, so an NTC, if I draw a resistance temperature graph, an NTC graph is going to look something like this. Okay, so let's look at low temperature. Low temperature, I have high resistance, right? So low temperature, I have high resistance. If the resistance here is high, if the resistance here is high, means the voltage, the potential difference here is high, and therefore V out is low. Okay, so the signal here will be a low signal. Can? But what happens if I have a high temperature? If I have a high temperature, the resistance here will be low. So in this case, if I have a if I have a low resistance here, low resistance, this means that the PD across here will be low, and therefore the V out will be high. Yeah. So when the temperature switches between a low temperature, a high temperature, the signal out also switches. Okay. So this is how you explain it. So we need to determine the value of R1. R1 is this fella. Yeah. So this is the situation. If we need V out to be 5 volts when the temperature is 40 degrees Celsius, and assuming that the supply voltage is 9 volts, and the resistance of the thermistor at 40 degrees is 6 kilo ohms. So I want to find out what value of R1 I should put into my circuit. Okay. So using these information, I find that R1 is 7.5 kilo ohms. So what we can do is we can put in 7.5 kilo ohms, and then um, the V out will be 5 ohms, 5 volts when the ambient temperature is 40 degrees. Okay. So another example, this is the corresponding thermistor resistance to the temperature. Okay, so determine the change in the output voltage as the temperature increase from 20 to 50. So what I first have to do is to find out what is the V out when it is 20. Okay, so at 20 degrees, it is at 10,000 ohms. Okay, 10,000 ohms, I find that at 20 degrees, V out using the voltage divider method is 1.6 volts. Okay, and then at 50 degrees, thermistor resistance is 4,000, and I find that the V out is 3.2. Yeah, so the voltage change is from 1.6 to 3.2 as temperature changes from 20 to 50 degrees Celsius. So as the temperature increases, the V out signal goes from a low to a high. You could look at it that way. Okay, so this is another example. Look through it, work through it. And at this point in time, I want you to pause the video and work through question 1 and question 2. Okay, do it now. Okay, so hopefully you did try it. Now, the first thing that I'm going to do is, of course, draw a resistance temperature graph. And I realize that since this is a NTC, okay, it's an NTC thermistor. At low temperatures, I'm going to have a high resistance. So at low temperature, at low temp, the resistance is going to be high. And this means that the V out is going to be high. Okay. And at high temperatures, the resistance is going to be low. So at high temperature, the resistance is going to be low. And this means the potential difference across a lower resistance is going to be low as well. Okay, so when the surrounding temperature increases, goes from low temp to high temp, so you got to write your statement when surrounding temperature increases. Don't be lazy like me. Write full temp and full increases. V out increases as well. Okay. So next, answers for question 2. So this is like a work. They gave you the answer that this is 3 volts here already. V out is 3 volts, and they want you to find at this particular temperature what is the resistance of a thermistor. Okay. So we have to use your voltage divider method. Okay, use your voltage divider method. So I've got 9 volts. Yeah, I've got 9 volts, and it's to be shared between these two. So this fella 330 takes 3 volts out of a total 330 out of a total of this 2. So I got to add this 2 in my denominator. From here on, it's math. So once you work it out, your RTH is 660 ohms. Okay. Don't know why the highlighter is not working well. All right. So I'm gonna pause the video here. Same thing. Assimilate what you have learned. And if you got any questions, email me. If not, I'll pause the video. I'll stop the video here before carrying on for the next component. Yep. So see you in a bit.